You know that feeling when you're just staring at a screen, waiting for an AI to reply, and you start to feel that creeping sense of impatience? Well, welcome to this explainer. Today, we're diving into the fascinating, incredibly high stakes engineering puzzle of why AI sometimes takes so long to think and how the entire industry is racing to fix it. We're talking about AI inference latency, the ultimate bottleneck that literally defines the difference between a wildly successful app and one that totally flops. But before we get into the technical weeds, let me ask you a question. Think about your own habits for a second. Honestly, how long are you willing to sit there staring at a blinking cursor or one of those little typing bubbles before you just give up and close the app? I mean, is it 10 seconds? 5 seconds? Well, the data is actually in, and the absolute breaking point is exactly 3 seconds. 3 seconds. If an AI takes any longer than that to respond, a staggering 70% of users will simply abandon the application and move on. In the world of production systems, where inference is happening in real time from millions of user requests, that is a massive, massive hurdle. And honestly, it gets even crazier. Every single extra 100 milliseconds of delay kills user engagement by another compounding 7%. To put that into perspective for you, a literal blink of an eye can cost an application a highly noticeable chunk of its active user base. It makes perceived speed an absolute necessity, not just a nice to have. So this makes latency way more than just a minor technical glitch. It's a massive economic battleground. Because of this urgent need for speed, the global model inference optimization market is just skyrocketing. It was valued at $4.2 billion in 2025, and it's projected to hit nearly $49 billion by 2035. That is a wild compounded annual growth rate, and it just shows you how absolutely critical latency optimization is to the whole AI economy right now. Okay, so here's our quick roadmap for how we're going to unpack this multi-billion-dollar problem. First, we'll unpack AI inference latency. Second, we'll look at time to first token. Third, accelerating token generation. Fourth, optimizing models for speed. And finally, hardware and system upgrades. Let's kick things off with part 1, unpacking AI inference latency. When you hit enter, it isn't just one big thinking step. It's actually a complex relay race happening behind the scenes in these crucial invisible milliseconds. First, you've got network transmission, the data actually traveling from your device to the server and back. Then queuing delay, where your prompt is just sitting in line waiting its turn. Next is data preprocessing, like tokenization. Then we hit the compute-heavy prefill phase, where the model digests your prompt. This is followed by autoregressive generation, which is super memory intensive because it spits out tokens one by one. And finally, post-processing formats everything and runs it through safety filters. Moving right along to part 2, time to first token. So if we want to make the AI feel instantly responsive to you, our first major metric is all about that initial feedback. We call this TTFT, or time to first token. This measures the exact time from the moment you hit enter to when that very first word pops up on your screen. This metric is dominated by that prefill phase we just talked about, where the model does a forward pass to process your input. What's wild is that for transformer models, this phase requires computing power that scales quadratically with the length of your sequence. So basically, if you write a super long prompt, keeping that TTFT low becomes a seriously tough engineering puzzle. Which brings us to part 3, accelerating token generation. Because let's be real, getting that first word out is really only half the battle. Now the system has to stream the rest of the answer without crashing into a massive bottleneck. And that brings us to TPOT, or time per output token. This dictates how fast the full response streams to you. Now, unlike the pre-fill phase, which needs tons of compute power, generating tokens one by one is entirely bottlenecked by memory bandwidth. For every single word, the system has to load the full model weights and what's known as the KV cache from memory. This is exactly why the rest of the sentence can sometimes just chug along slowly, even if it's running on a super powerful machine. To fix this, engineers are totally overhauling how servers handle traffic. In the past, servers used static batching. This meant all requests in a batch had to finish before any new ones could start. It's kind of like waiting for the absolute slowest eater at a restaurant before anyone can leave the table, leaving incredibly expensive GPUs sitting around completely idle. Now they're tossing that out for continuous batching. This dynamically swaps requests in and out on the fly, constantly feeding the GPU and maximizing its utilization. It is a total game changer. Another totally ingenious solution to these memory bottlenecks is called speculative decoding. Think of it like this. You've got an eager, super fast intern drafting up a quick reply, while the boss, the massive target model, rapidly signs off on it. A small draft model proposes a bunch of candidate tokens really quickly, and then the massive target model verifies all of them at once in a single parallel pass. If the intern was right, you just generated multiple words in the time it normally takes to generate one. You get a 2 to 5 times speed up, literally cheating time without sacrificing a single drop of accuracy. All right, part 4, optimizing models for speed. So those last tricks were great system-level hacks, but what if we just make the AI's brains smaller and faster before we even put it on a server? Developers are doing exactly this using the PKQ compression pipeline. It's a neat 3-step process. First, they prune, removing redundant parameters or whole attention heads, literally trimming the dead weight. Second, they distill, training a smaller student model to mimic the larger teacher model. And finally, they quantize, which just means reducing the numerical precision of the underlying math. And I have to say, the real showstopper here is that last step, quantization. Get this, by just reducing the numerical precision, like shrinking a 32-bit floating point down to an 8-bit integer, you can actually shrink a model by 75%. Doing this cuts your inference costs in half, and miraculously, it still maintains 95 to 99% of its original accuracy. When you stack all these optimizations together, you can slash overall inference costs by 80% or more. It's absolutely brilliant. And that brings us to our final section, part 5, hardware and system upgrades. Because, let's face it, no matter how tiny or optimized your model is, it still needs serious physical infrastructure to process this fire hose of data at lightning speed. And the hardware industry is definitely delivering. We're seeing incredibly specialized hardware like Google's TPU v5, which is pushing a 4 times performance improvement for transformer architectures. For mobile and edge devices, NVIDIA's Jetson Orin handles an astounding 275 tera operations per second. Plus, this hardware is being paired with lightning-fast frameworks like VLLM to maximize server throughput and distributed inference strategies that split massive models across multiple GPUs so no single chip gets overwhelmed. All of this raw power and innovation is pushing us toward what I think is a beautifully elegant setup, the edge cloud hybrid future. Imagine a system where your smartphone uses a highly optimized small language model to handle your everyday tasks instantly. We're talking literally zero network latency. Then, only the toughest, most complex queries get routed up to the heavy-duty cloud servers. It's the perfect balance, giving you the absolute lowest latency for common tasks while keeping the raw power of large models available right when you need it. Which leaves us with one final, kind of mind-bending question for this explainer. We've seen how latency entirely dictates user engagement and how the tech industry is throwing tens of billions of dollars at quantitation, speculative decoding, and next-gen silicon just to shave off a few extra milliseconds. So, as these multi-billion-dollar optimizations compound over the next few years, what exactly happens to our digital world when AI delays effectively drop to zero? When interacting with an AI feels just as instant and just as natural as your own thoughts? Because make no mistake, that is the exact future the industry is racing toward. Thanks so much for joining us for this explainer, and we'll catch you next time.